Hello everyone, welcome to our talk. My name is Jiahui Fan. I'm very glad to introduce our paper at SIGGRAPH 2023, the neural biplane representation for BTF rendering and acquisition. In this paper, we present a small but generalized network for different kinds of BTFs with a good balance between efficiency and accuracy. Our universal network can also achieve a lightweight BTF acquisition approach. Before introducing our paper, let's first review some backgrounds. The bidirectional reflectance distribution functions, also known as BTFs, have been widely studied through the past decade. The analytical formulation of them granted us huge flexibility and controllability at the cost of biases, while the measured ones can faithfully recover the appearance but require many efforts in utilizing them efficiently. When we like to extend the dimensionality of the BTFs, we add the spatial axis into the formulation, and then we got the spatially varying materials. Naturally, two different kinds of materials are derived from those two kinds of BTFs, and they also had inherited the advantages and disadvantages of them. So why would we choose BTFs in the rendering? Firstly, BTF provides more vivid and realistic appearances. Also, the generalized formulation of BTFs can ideally go with many different and complex effects. For example, the parallax effect and the subsurface scatterings. However, we still need to note the inconvenience in acquiring and utilizing them. Actually, the main challenges lie in the following aspects. Firstly, to process the BTF data, the basic choice is to tabulate them, which is of course storage consuming. Some approaches leverage PCA or dictionary learning to reduce the dimensionality of the data, but still takes a long time to finish compression. Also, in order to calculate the eigenvectors, they would always like the data to be complete and structured, which is sometimes not a condition in practice. Some recent work using neural networks also focus on the BTF compression, and we will discuss them later. Apart from the compression, the acquisition of BTF itself is naturally difficult. We either afford the expensive and complicated equipment to capture thousands of photographs and process them, or we suffer from the inaccuracy and ambiguity by using SVBIDF models to fit those real-world BTFs. Therefore, the acquisition of real BTF data is still out of the realm of lightweight approaches. Now let's review some previous work in representing BTFs with neural networks. Some methods train a single network for each BTF and render them. We call them the overfitted models. The tailored networks can provide the best accuracy at the cost of retraining for each new material. And there are also generalized models that can be trained once and applied to any new materials. Some of them even support more complex surface appearances like layered materials. We call them the universal models. The universal models encode priors well into their feature space and are capable to reconstruct unseen materials with trained materials. However, the drawbacks are either less accuracy or relatively longer compression time. Therefore, our target is to make the model as small as possible while still universal. Also, we need to speed up the compression with acceptable accuracy trade-offs. We start from a very common structure from previous work. A latent texture that encodes every texels, and it will curate a universal decoder with the angular information to get the reflectance values. In this case, the network always needs to be bigger to generalize over the samples and have the power to deal with both spatial and angular variations, which is relatively difficult. We observe that many texels share the similar properties. They might be painted with similar colors or made with similar materials. It's not wise to let the network just treat them separately as individual ABRDFs. Therefore, we need to somehow notify the network about their commonality. Also, when we talk about angular information, the traditional way is that the decoder always takes the full query as input. However, we can still notice that the half vectors are actually giving more variation to the BIDF lobes than the difference vectors. So we should treat them differently. Here we summarize our design. Generally, we use a biplane feature to describe a given BTF. It consists of two feature planes, the H-plane and the U-plane, representing the spatial and angular variations respectively. Therefore, with those explicit feature vectors, the network can easily recognize BTFs with similar spatial and angular information. Note that the half vector is represented by features, while the difference vector is directly accepted by the network, since the different vectors encode fewer variations. This design reduces the complexity of the network and makes it generally easier to learn. Our design also has a good scalability. In order to deal with some complex effects like parallax, we introduced the neural offset module from previous work to enhance the representation of our model. Please refer to our paper for more details. Since our universal network can encode the prior of different BTFs, we can therefore achieve a lightweight BTF acquisition approach with only 20 cell phone flashed photos, instead of exhaustively get the full measurement of this angular information. Note that all data points are under collocated lightning, which means the difference vectors are always zero. However, our universal network can still obtain the biplane features of that BTF by optimization. Also, to prevent the blank areas from the optimized H-planes, we use the linear combination of H-planes in our dataset to fit the target BTF. Here we show some results. We compare our model to previous work, the unified BTF encodings. Our model generates closer results to the reference with and without the offset module. The learned biplanes also shows the angular and spatial information for those SVBIDFs. We also test our model on real-world BTF datasets. On those captured data, our model still outperforms previous work, even with much sparser and unstructured data as input. In this figure, we show the results for lightweight BTF acquisition. The network produces plausible renderings under all those unseen view and light directions. The last, we shall conclude our paper. First, we present a small but universal network for BTF representation and rendering. We trade off between generality, accuracy, and inference for a good balance. Second, we design two explicit feature planes for both spatial and angular domains. At last, our universal model achieves a lightweight BTF acquisition approach. The main limitation of our work is its less precision compared to some huge models, since we trade it off and do not focus on some extremely specular materials. Also, since the number of real-world BTF dataset is limited, we also cannot process some exotic materials that do not exist in the training dataset. Thanks for your attention. Please feel free to have any questions.